In this video, I'm actually going to take sort of a small diversion from our tensors and talk a little bit about manifolds. So, manifolds, which are a sort of topological object. So, this is from topology, and I'm not going to go through sort of all the sort of point set topology and everything to get to a manifold. I'm just going to sort of propose a manifold and just tell you sort of what it's like. And so we have a manifold, and I'll just draw it as kind of a circle here, and it's M. And in this video, I'm going to start a little bit more general and just kind of ease into something a bit more concrete, but I'm not even going to be as general as probably what most treatments of this subject would be, because I'm going to say that this is a manifold in 3 dimensions. And so this is a three-dimensional manifold. And so you could imagine it, this could be, I'm drawing it as a circle just to tell us that, its shape is a little bit amorphous. We don't have like, a sort of a concrete shape for it. I could have drawn it like this or something if I wanted to, but so I'm just going to draw it as a circle, but just bear in mind that it doesn't really have sort of a concrete shape. And so because it doesn't have a concrete shape, if we want to talk about a point on this manifold here, and we want to give it coordinates, well, if you have a weird shape, if you have, some shape that looks like this, and this is your space. How do you put coordinates on that? We'd probably think if we embedded it in some higher dimensional space, so we put it in some higher dimensional space, and then we could talk about points on it as being distances from the origin. But if we want to talk about sort of the intrinsic geometry of our manifold here, what we have to do is what is called a chart mapping. And so we take a portion of our manifold, and I will actually draw sort of a circle here in green. So this is sort of a neighborhood of this point P, a neighborhood in the sort of topological sense, but we can think about it in the intuitive sense that it's just all the part of the manifold around that point. And so we'll call that U. I think that's kind of standard when talking about manifolds. We'll call this U. And so we can have a chart map, which is just a function. It's a map that takes points inside U. And so we'll call this chart map, we'll call it gamma, and it actually puts it into a coordinate system. So this is 3 dimensions, so we'll have a 3-dimensional coordinate system here. So Z, we have X, and we have Y. And so then we could have P sort of in our coordinate system here, and it would actually have an X, Y, Z coordinate. And so our gamma is a map that takes a point P and maps it onto an X, Y, Z coordinate in this chart over here of U. So this is the chart of U. And of course, we could take this chart and map it back to our manifold, and this is the inverse of gamma. So it'll be gamma with a superscript -1 there. And so this is, it's called a chart because that's kind of what it is. It's like we have this book here that tells us points on our manifold. It could be, you could think about it like a chart of coordinates on the planet Earth. if you want to look at, like, if you're doing like geocaching or something, if you want to look at sort of the coordinates of things on the planet Earth, you'd have a chart with those coordinates on it. And of course, you could take those coordinates and sort of, you know, give it each, give, give it sort of a three-dimensional graph of those, and that's kind of what we're doing here. And so this is a chart of this little section of our manifold here, which we call the U. And so it's sort of giving coordinates to each of the points on this manifold, or at least each of the points in our chart map here, U. And so it's sort of giving, well, like I said, it's giving coordinates to it, because we don't have coordinates here in our actual manifold. We have to sort of map those coordinates over here. And of course, you can have other places in here too. So you could have some other thing here, and maybe we'll call this U sub 2, and so we'll call this one U sub 1, which makes this the chart of U sub 1. And so U2 would have its own chart, and you can see that there can be overlap there. And in fact, this kind of thing is actually very common, and I actually have an example of that down here. So this is how we sort of chart the 2D surface of a sphere. So we have our North Pole up here, and then we just sort of make a straight line from the North Pole and go through, and then we're hitting this point here, and then we kind of put that down onto a flat surface, the flat surface being tangent to our P0 here, and then we can do the same thing with this point here. And what we find out, so what you'll see is, if you want to chart, this point here, then you have to make a line that's like, really long, and it goes, sort of way off onto our 2D surface, like way over here. But then you see, if we try to chart our very North Pole, you'll get a line that goes just completely horizontal, and it never actually reaches our flat space below the sphere. And so that point there doesn't actually get charted. And so we actually need to make a second version of it. So that would be with the sphere here. So we have our sphere here, and then we're looking at a sort of flat surface on here. Then we sort of do the same thing, but from the south pole. And so we end up with two charts. So the one from which is sort of at the North Pole here, then the other one at the South Pole here. And they overlap everywhere on the sphere except at those very poles there, which those poles can't be mapped onto the same thing. And so we end up having to have two different maps. And so that's an example of where you would need something like this, where you would need two different maps. And so in this sphere example, everything is in the overlap here except the two antipodes, the North Pole and the South Pole of it. But anyway, that is sort of how a mapping works. So there are a few other things we can do. So the first one is we can actually define functions on our manifold. And so we take the whole manifold here, and we have some function, which I'll call f. And there can be multiple functions, and I'll sort of get into that in a little bit. And this maps it to some real number. I mean, you could have it be a complex manifold if you wanted to, but I'm talking, like I said, a little bit more concretely than you will probably find in a lot of treatments of this. And so that's just a real number. So that's just the real number line. So it's just a line, and we have, -2, -1, and 0, and 1, and 2, and so on and so forth. And of course, everything in between. And so there is, we can take all the points on the manifolds, or point P, and or we could have some other point Q here, and everything in everything in between and everything all around. And this function takes each of those points and maps it onto the real number line. And we can actually find out that there are these things called level sets, where say we have our point P here, and then we have another point over here, R, and they both have the same value with F. And in fact, and I'll even put this in purple here, so we have this circle here, and everything on that circle, maps to the same point on the number line. And then we could have so some other points here in blue, and each of those map to some other point on the number line here. And so those are called level sets, where the function at everywhere on that line is the same. And if you've watched my other videos, you can probably tell that that looks very familiar to our sort of covariant vector space, but I'm not going to get into that right now. So we have that. So that's a function that maps things from our manifold onto the real number line. But we could also have a function where we take the real number line here, and so that's the real number line, and I'll call this lambda. I'll call it lambda, and so it takes points from this and then maps it onto our manifold here, and so that maps it here. And I'll put this, so it maps every point on the real number line to some point on our manifold, and so that would actually make a line on our manifold. And I'm going to purposely have that go through P, go through the point P there. And so, this point on the number line here would map, say, to that point on our line there. That point on the number line maps to, that point there. And usually what you do is you set 0. So if you're interested in this point P, you have the point, or the number 0 on our line here map to our point P right there. And so these are sort of all the different things that come with a manifold. So we can map lines on here, which is parameterized by this lambda. So it's parameterized by that lambda. And we can have functions on our manifold that take every point on our manifold and maps it to the real number line. And we have this chart mapping, which actually gives coordinates to each of the points on our manifold. And so then there are a few different things we can do. So the main ones that we're going to be kind of interested in here. So if we want to take our line and put it onto our manifold here, and then we want to find out what the value of the function is everywhere on that line, then we have to then take that every point on that line and then map it with our function over to here. And so that is sort of going through the manifold, just going from this lambda to this number line over here. And that would be essentially having our function f, which is a function, and I don't think so this function here for the line I'll call beta. So I'll call that beta because sometimes my alphas and my gammas can start looking the same. I don't want to mix it up with our gamma here. So it's a function of beta, which is a function of lambda. And you'll oftentimes see this too as f, and then this little circle here. I'll try to draw it more like a circle, and then beta, which is just saying that f is a function of beta, and beta is a function of lambda. And so this tells us that we're sort of going on a path into our manifold, but not stopping there and then going down over to here. And of course, if we want to talk about points on that line, then we actually have to go through our chart mapping here. And so we actually need to add sort of a second thing, which is taking our beta, so going from here into our manifold and then into this, and then going from this back into our manifold and then down here. And so uh, going from beta into our chart there, so what we do is we actually have beta, which is a function of lambda, and then we have our gamma as a function of beta. But then we also want to, so we do this first, and then I'll even do the little circle notation here. Then we want to do our f, which is a function of the coordinates in our chart map here. So that'll be a function of our inverse gamma here. And so we end up with this. So this gamma and this gamma inverse here, you can sort of think about as canceling out. But we have to get coordinates for each of these things, which means we have to go into this chart map here in order to do that. And so this gives us our sort of full map going from lambda here all the way over to our real line, which is the output of our function f. All right, and so now let's get a little bit more concrete about this. This is, I mean, like I said, this is probably a bit more concrete than you'll find in a lot of treatments of this subject. But let's get even more concrete just to make this thing a little bit easier to think about. And so I actually, so I have this down here. And so I'm thinking about this as like a neighborhood. And we'll think about these numbers here. So the lines are streets. The numbers here are addresses, for houses on these streets. So these are streets with houses. And so, I mean, this is already kind of in a nice sort of grid pattern here, but you could imagine that each of these streets could, we could have, this be our main street, and then each of the streets is sort of, some weird curving thing, if you're like in the suburbs or something. So we could have weird curves like this, where each of the numbers, so 11 and 12 and 13, don't align up nicely like this. And then we could actually sort of make a chart map going from this down to something that looks like this. And so we end up with this sort of nice chart mapping like this. And so, I mean, we could even take this one. So if we, and I'm actually just going to erase this up here just because this is probably going to get pretty messy as it is. But so we could take a chart map and, we could plot each of these points onto some x, y plane. So we have x and y, and we could map each of these onto here, so that's our gamma, and then we could map each of these onto here, which is our gamma minus 1. And we could define functions on this neighborhood. So maybe we could have a function h, which is a map of each house, and we'll say that's addresses, and we'll call that A. So A for addresses onto say height. So the height of each, or I guess the average height of all the people living in each house. Or we could have some other mapping, which is A for each address, and that gives us the age of people in each house. So we go to each house. Each house is sort of like a point on our manifold, and we map that to the age. And so the age, of course, is just numbers on the real number line. So 0, 1, 2, 3, and so on. And so we could map, some the people in this house. Uh, I mean, let's just for simplicity's sake, each of these houses has a single person living in it. So we could map the age of the people of the person in this house, to some point on our number line. We could map the age of people in this house to some other point on our number line. And so we could keep doing that for each of them, and that is a function for age. Um, and, like I said, we could do it for height as well. But the one I am going to use, and so I'll call it the money map, and so that maps the address to the person's income. And so we could, for each address, we could say that each person has a specific income, and so that is our function on here. And for simplicity, we could even say that, say, the people here in the bottom left corner, so the people down here are poorer, are poorer, and the people up here are wealthier, are wealthier. And so we could actually sort of define level sets on here where, say, we have, and I'll put this, I'll do it in blue. So so this right here is some income. Maybe we have some other income like this, some other income that goes through here, and some other income. So all the houses on these lines have the same income. And so we have something that looks like this. And we could kind of keep going until we get to here where, this is the McAllister house over here. And so then we could actually define a line on here, which is the line. So it's a line on here, which is the line of the path of the wet bandits who are going and robbing these houses. And so say the wet bandits, say they live over on this side of town, and so they start over here and they rob, house 11, and then they rob house 23, and then they rob house 37, then house 47, and finally they hit house 60. And so this is our line that is the path that the wet bandits take as they sort of rob houses through this street. So up here we have the McAllister house, and so they rob their way through this neighborhood. And so what we can do is we can actually, so our function, which, so the function is income, and I think I put that as a money sign. So the function, which is a money sign like this, is a function on our manifold, which is the neighborhood. And so that is equal to f of our inverse gamma, because our gamma, so each of these houses is plotted as a point here in our chart over here. And so say house 11, and like I said, this neighborhood I already have kind of nice and straight, so the charting probably isn't that helpful because house 11 would be right here, and house 21 right here, and house 31, house 41, house 51. And so this, so gamma inverse just takes that point and puts it back on our manifold. But like I said, each of these streets could be, really curved, but in our chart it would still be sort of this nice grid pattern like this. And so even if the streets were all curved and bendy and everything, our chart would still be like that. But we in our manifold we don't have nice coordinates. So in the chart we have a nice y coordinate and a nice x coordinate for each of these houses in our neighborhood. The neighborhood being the manifold, and so this tells us that this. I think I put F there. That's actually what I use in my notes, but this would actually be our money sign function here. So our function that's a money sign, and it's a function of x and y, because the x and y come from our chart mapping, and so we can think about it as a function of x and y. And of course, then the line which is the path the wet bandits take, and I'll actually sort of retrace this in red so I can sort of talk about things using different colors. So the wet bandits take this line here. And so the line is, I mean, maybe the line is parameterized by distance between the houses. And so, uh, well, yeah, so we can think about it as so we have our line here, and that is our lambda. That is our lambda, and that is being mapped onto our manifold here with our function beta, which is a function of lambda. And so lambda is, like I said, sort of the distance between different points, different houses on here. And so, the wet bandits make this path through here, and it takes different distances between each of the houses. But in order to do this, we first have to actually map it onto here. And so what we do is, we first map it. Onto our manifold here, and then from the manifold we actually map it onto here. And so we first map it into the manifold, and then we take the gamma, and I'll actually keep gamma here in black. So we have our gamma, which is a function of our beta lambda. And so we have this, and then from there we want to then map it back onto our manifold, which is what this gamma inverse does. And then from the manifold we want to map it using our money function here, which so well, I'll get into sort of the interpretation of that here in a little bit. And so what we have then is we have our money function here, which is a function of our inverse gamma, because this inverse gamma is taking it from our chart back onto the manifold, and then we actually want to then do this operation, which is just essentially the same operation as just taking a function of a function. So this will be then of our beta, which is a function of lambda. And so you could actually think about this as being sort of like the $ function of our inverse function, which is a function of our gamma, which is a function of our beta, which is a function of our lambda. 3, 4. So it ends up being sort of like this. It's just a bunch of nested functions together like that. And so we can actually say that this is our income function, which is a function of x and y, because this gamma inverse just takes it from x and y back onto our manifold, and then that uh, we compose that. Well, so we have our gamma function here, and this we'll call the gamma function of x for beta, which is a function of lambda. And so this is just the sort of x component here of our gamma. And so what we're doing is, once again, so this beta we're mapping onto our manifold here. And then this right here is just taking that house on the manifold and giving us the x component of it. So it's just giving us this component of, say, we're looking at house 11, which is this one right here on our chart map. It's just giving us the sort of the x part of it. And so that is the x part of it. And then we also want, actually that wouldn't be plus, would it? So say we have this. So this is sort of like a tuple, a two tuple here. And so then we also have our money function here, which is x and y composed with now the sort of y part of this gamma function, beta of lambda, like that. And so that is sort of our n tuple there. Well, it's a two tuple. It's an n tuple where n equals 2. All right, and so we can actually take the derivative. So the derivative of f of x and y with respect to lambda. And so we sort of have to, well, once again, I put f here. So I'll just say that it's d of our money function here, which is a function of x and y. And we want to take that as with respect to d lambda, which means we have this sort of whole nested hierarchy of functions here. And so what we have is we have the partial of our f. Once again, I used f. That's how I have it in my notes. I've this s, or this money sign, was a bit of improv on my part. So x and y with respect to dx. And then we're doing the chain rule here. So now we have dx with respect to d lambda. And so this one we can do an ordinary derivative because it's just respect to a single variable right there. Had a little bit of a brain fart, but anyway, then we also have the partial of our money function here. That's a function of x and y with respect to y, and then dy d lambda. And so we end up with this. And so we can think of, so the x, of course, so the x, so we could also think about this like this. So our partial of the money function with respect to x and y, then the partial, so the x is actually well, it's well, this would be, in our map, or our chart rather. And so this would be sort of like I guess the gamma inverse uh, the gamma inverse of x, and then we have our d, and this would be sort of the gamma inverse of x with respect to lambda. Put that x in the exponent there. I didn't mean to do that. All right, so that is just minus 1, and it is the function of x there. And so that's just mapping that onto the back onto the manifold. Then of course we have our d, and that is the money function x and y with respect to -1 and y sort of d inverse y over d lambda. But anyway, let's, I don't want to confuse things too much. The thing I'm trying to get at here, though, is that what we see here, this is sort of in the form of vector components, isn't it? And so if we actually get rid of our function and we just have our partial with respect to x, dx d lambda plus our partial with respect to y dy d lambda. This looks a lot like, well, we could actually even put it like this. So the partial with respect to x1 plus, well, not the plus first, so dx1 d lambda plus the partial with respect to x2 times dx2 d lambda. And so then we could even put this into the sort of Einstein summation convention. And so you will often see these written as just the partial with a 1 down here, and then this would be the partial, or this part would be the partial with a 2 down here. And then if we combine those together, we just get the partial I like that. And so you'll often see this as the partial I, and then these dy d lambdas are just components, and so you can actually have these as well. I guess we'll think about this over here. So this dx d lambda, this dx1 d lambda, and dx2 d lambda, you can think of as sort of dx I d lambda. And so we would have dxi d lambda, and of course this is summed over, so I equals 1 to whatever we want it to be. So for us, I have it at n equals 2, but it could be any n. And so this is di, and then we could just turn this into, because it's just going to be some number, so we'll call it vi. And so this di here is like a basis vector, and you know it satisfies what we think of as basis vectors. It has a direction, you know, because when we take the partial with respect to x, we end up with something pointing in the x direction. And when we take the partial, so that's the partial with respect to x, and then if we take the partial with respect to y, we have something pointing in the y direction. So those serve as bases. And then this v here works as components. So components. And so, you know, when we have a vector, it's just adding so we just multiply a component by each of these basis vectors. So we would have vx and then vy y would give us, and in fact I will, just to make things a bit clearer, I will change that into green because I don't want to confuse it with our basis vectors. So we have so we have that component there, and then we have the y component like that, which would be our vx times our dx here, and then we have our vy times our dy here, and this gives us, some vector here. This gives us some vector that goes up to there, and so this vector is our vi d. That looks like a 2 vi di like that. And so this gives us sort of a vector space, and this vector space is called the tangent space. And so the tangent space, so we can think about it like this. So, I mean, there is going to be a sort of tangent vector to everywhere on this line here. I'll change back to black. Everywhere on this line, there's going to be some tangent vector. And that tangent vector is going to be, well, it's going to be these dy d lambdas here, sort of the dx and dy, or the dx1 d lambda, dx2 d lambda, all the way up to dx n d lambda. Or if we started at x at dx0, it'd go to dx n minus 1. But anyway, so there is sort of a a vector at each point on this line here. So this line is actually giving us, well, if we're talking about the tangent space, we're talking about sort of every line that could go through a point. So if we think about this house 37, we could think of every path the wet bandits could take, and they could take a path through it that looks like that, that. They could, take some weird path like this that goes through it. They could take another path that looks like this that goes through it. And so each of those paths will give us different components. And so each of these components is dependent on the path. But because we took out the function, these basis vectors sort of stand alone. But we could add a function in, and it would give us some new value. It would give us some different value for that. And we could think of the function essentially as maybe how much money the wet bandits, the function is how much is the income, and so the function with the path would be sort of how much money the wet bandits actually make by robbing that path. So given that function and given a certain path that they take, this will tell us sort of how much money the wet bandits actually make as they take a specific path through there, because the specific path will give us specific components here, and so these components are dependent on sort of that line going through our manifold. But anyway, so I hope this video kind of helped you understand this idea of what's called coordinate bases on our manifold. And it's important because, this is sort of the language that gets used in a lot of differential geometry, because differential geometry is interested in manifolds. So differential geometry, which is, that is what you're doing when you are doing, for instance, the Einstein equations, when you're, solving for the Ricci tensor and all that stuff, which is what I'll be talking about in the videos to come, and that's why I thought this video was kind of important, because it's kind of a difficult but important topic to understand. And so differential geometry, as I said, is interested in manifolds. And so when we are talking about manifolds in general relativity, for instance, we're talking about manifolds, that have a metric tensor, or it can have multiple metric tensors. It can be metric tensors at every one of those tangent spaces. And so the tangent space being sort of well, if we're looking at a point, so this point 37 here, this house 37, the tangent space is sort of all of the lines that go through it, which gives us our components for the vectors in that tangent space. And then this basis vector, which is just this partial differential here. But anyway, the idea is that, tensors, and then this idea of manifolds in the sort of basis vectors, the coordinate basis and so forth, are sort of, entwined with each other quite a bit. And so it's important to, if you want to sort of understand the general relativity equations, to understand this idea of a manifold. But anyway, I hope this, like I said, this more concrete treatment of manifolds was at least somewhat helpful. Once again, going by that philosophy that, math is one of those things that you don't really understand, you just sort of get used to it. And so it's important to sort of, expose yourself to numerous different sources. And I'll actually leave a really good source for thinking about manifolds in the description down below, by one of the YouTubers that, well, I've left links to them in the description of all my videos, but they have a really nice manifold playlist, and they have a video that's actually like, over 2.5 hours, that is going over essentially what I just went over in this video. So I went over it, I mean, this is already a long video, but I went over it, quite a bit more quickly than what this person did. And I keep saying this person because they have a really hard name to remember. It's something like XYLYXYLYX or something like that. But anyway, I highly recommend, if you're interested in getting into manifolds, and particularly building up to manifolds from point set topology. That's what he does in his playlist. And like I said, he has a single video that's like over 2.5 hours long, that goes into a lot more detail and a little bit more rigorously, well, quite a bit more rigorously, and more generally than what I did here in that playlist. So I highly recommend that if you, if my video here only just sort of whetted your appetite for this. But anyway, I don't want to keep rambling. I hope you found this video helpful, and I will see you in the next video.